My name is Michael. This is Jonathan and Sasha, and we've developed or are developing an in situ manufacturing method for LTCC-based heat exchangers. So I'm going to give the floor over to Sasha, who's going to give you a little background on the project.
So NASA has a need for self-sufficient space stations and bases in support of their future missions. This can be achieved with ceramic manufacturing. Basically the same way first tools were made, we can use the natural soil on the moon and on these different planets in order to create these devices. Ceramic manufacturing is a proven technology. It's been used to create things from simple pottery to things as complex as micro-electromechanical devices being used in the industry today. It'll be a simple process that can be easily duplicated in space conditions, and lunar soil is readily available, and most of the space material has a glass and ceramic composition that makes manufacturing feasible. This is an overview of our materials and costs. We purchased 1 kilogram each of Martian and lunar regolith simulant, as well as a total of about 129 man-hours used to operate the different devices and research, and approximately $4,200 so far that's been spent. This is some of the global companies that are working to produce microchannel heat exchangers. For example, Daikin is a global leader in air technologies, and Sapa Group is a Norwegian company that's actually developing a similar design to ours. It's a flat, rectangular heat exchanger with microchannels running through it.
All right, so just a little background on the applicability of this project. Essentially, these devices can be made anywhere where there is a soil that has a ceramic and glass phase composition, which is very often. We're proving it through 2 types of soil. One of them is going to be the lunar regolith, the other is going to be the Martian soil. They're both simulants, by the way, they're not actually from the moon, from Mars. And both of these are steps towards developing ways to live off of the land on the moon and Mars, and ultimately beyond that. This is our initial test design. As you can see, everything's a millimeter, so it's pretty small. It's a very small device, so it'll fit on one finger. The channel is 0.5 millimeter tall by 5 millimeters wide, and that channel breaks down into 7 different channels. This essentially was made to determine performance benchmarks and set up the CAD model for the machines that actually do the punching and cutting in the materials labs. This is an overview of what the project involves. Essentially, we're doing LTCC development first to figure out if this is possible with tape products. Then we're taking the simulant-based the soils, and we're characterizing them and ultimately making tape, and then we're going to follow the same LTCC development for those heat exchangers. Finally, we're going to take the heat exchanger and put it into an optimization program and hopefully get an optimized product. And right now, this is our current progress. We've characterized the lunar regolith. We're at the point where we're doing XRD and SEM analysis on the soil. For the LTCC, we've done the fin and via punch. We've actually got to the point where we've stacked, laminated, and fired, and we have the finished product, but we haven't tested it yet. And the initial model has been virtually built and determined, but the characteristics of performance have been determined in ANSYS software.
The main milestones of our project are going to be the characterization of the lunar and Martian regolith. The lunar regolith has been mostly characterized already ahead of schedule. We will then be making sheets out of the regolith simulants. That should be complete by July 18th, and the LTCC is already in sheets. The optimization process should be complete by October 10th. For future considerations, if we have the time during the project, we're going to make the regolith into inks and make that into something that can be implemented in the NScript system for 3D printing so that we can do additive manufacturing, and so it can be built in situ wherever they may be. The final goals for this project are to create a method for lunar and Martian regolith characterization, which is mostly complete at the moment, and then to be able to construct a heat exchanger from LTCC, lunar and Martian regolith. Our optimization goals are to have a hermetically sealed device, minimum pressure losses, and maximum heat exchange. All right, thank you very much.
Any questions?
Questions?
I have a comment on that last slide. Can you bring it back up again? Yeah, where it says final goals to the right, can you either change the fonts or the background of that? So we
Yeah.
can read
Do you want me to do that now?
it? No.
Okay.
For the final presentation.
Yeah, okay.
Do you agree with that?
Oh, absolutely.
Thank you.
It doesn't look this way on a personal computer. I think it has something to do with the projector and the light in the room.
Well, that's why
So,
you're
yeah,
doing this.
yeah, we learned.
Yeah, exactly.
Any other questions or comments?
Yes.
What was your criteria to assign $100 and some dollars to SolidWorks modeling? Sounds like based on the license or something?
No, it's an average about $32 for a junior mechanical engineer. So based on the amount of time that was used for each component, you just multiply that by that average.
Any more questions?
Thank you.
Very much.